From the phone in your pocket and the ATM you use, to smart TVs and complex industrial machines, touchscreens are absolutely everywhere. We interact with them every single day, often without a second thought. But have you ever stopped to wonder how they actually work? And did you know that the screen on your smartphone is fundamentally different from the one at a public kiosk? Not all touch screens are created equal. In this video, we're going on a deep dive into the fascinating world of touch screen technology. We'll explore the different types, break down how they function, and uncover what makes each one unique in terms of performance, durability, and cost. By the end, you'll have a whole new appreciation for that magical piece of glass you tap and swipe all day long. So, what exactly is a touch screen? At its core, a touch screen is an interactive electronic visual display. It's a brilliant combination of two technologies, a display like an LCD or old panel that shows you the image, and an overlay of touch-sensitive sensors. When you touch the screen with your finger, a stylus, or another object, these sensors detect the location and pressure of your input. This information is then sent to a controller, which interprets your action whether it's a simple tap, a swipe to scroll, or a pinch to zoom. It's this seamless fusion of seeing and touching that transforms a simple display into a dynamic, interactive interface, allowing us to directly manipulate digital information. Let's start our journey with one of the originals, the resistive touchscreen. Imagine thin, flexible layers, usually made of plastic or glass, coated with a conductive material. These layers are separated by a tiny air gap. When you press down on the screen with a finger, a gloved hand, or even the back of a pen, you physically push the top layer down until it makes contact with the bottom one. This contact completes an electrical circuit at that precise point. The controller then measures the change in electrical current to determine the exact coordinates of your touch. Because they rely on pressure, resistive screens work with almost any object. They're also inexpensive and quite durable, which is why you still see them in rugged environments like factories, retail point-of-sale systems, and many ATMs. However, they have lower image clarity due to the multiple layers, and they generally don't support multi-touch gestures. Next up is the technology that probably powers the device you're holding right now, the capacitive touch screen. Unlike resistive screens that rely on pressure, capacitive screens work with something all humans have: a natural electrical charge. The screen is coated with a transparent conductive material like indium tin oxide. This coating maintains a constant electrostatic field. When your finger, which is also conductive, touches the screen, it disrupts this field by drawing a tiny amount of electrical current to the point of contact. The screen's controller detects this change in capacitance and pinpoints the location. This method allows for incredible sensitivity and high image clarity because there are fewer layers obscuring the display. It's also what makes smooth multi-touch gestures like pinching and zooming possible. The main drawback: it requires a conductive input, so it won't work with a standard glove or a non-conductive stylus. That's why your smartphone, tablet, and modern laptops almost exclusively use this tech. Now for something a little different, the Surface Acoustic Wave, or SAW, touch screen. This technology is pretty clever. It uses ultrasonic sound waves that are too high-pitched for us to hear. Transducers placed along the edges of the screen generate these waves, which travel across the surface of the glass in a precise grid pattern. When your finger or a soft-tipped stylus touches the screen, it physically absorbs a portion of these waves. Receiving transducers on the opposite sides detect this interruption. The controller then analyzes where the wave was disturbed to calculate the touch location. Because there are no metallic layers on the screen itself, SAW technology offers superior image quality and clarity. The main downside is its vulnerability to contaminants. Things like water droplets, dirt, or even a bug on the screen can accidentally block the waves and trigger a false touch or prevent a real one from registering. This makes them best for clean, indoor environments like public information kiosks and certain medical monitors. Let's move on to infrared, or IR, touch screens. This technology creates an invisible grid of light across the display. How? It uses a frame around the screen that is embedded with pairs of infrared LEDs and light detectors on opposite sides. The LEDs shoot beams of infrared light across the screen to the detectors on the other side, forming a tight grid. When you bring your finger, a pen, or any other object to the screen, you physically block some of these light beams. The sensors instantly detect where the beams have been interrupted, and the controller triangulates the exact X and Y coordinates of the touch. A huge advantage of IR screens is their durability. Since the touch sensing technology is in the bezel around the screen and not on the glass itself, the display is protected and can be made from very tough material. They also work with any object and support multi-touch. However, they can be a bit more expensive and are sometimes affected by bright sunlight, which can interfere with the infrared sensors. You'll often find them on large format displays, interactive whiteboards, and outdoor kiosks. Similar to infrared, we have optical imaging touch screens. Instead of a full grid of LEDs, this technology typically uses just a few infrared cameras and light sources, usually placed in the corners of the screen's bezel. These cameras constantly monitor the surface of the display. When an object like a finger touches the screen, it creates a shadow or blocks the light from the camera's perspective. By analyzing the images from at least 2 cameras, the system can use triangulation to calculate the precise size and location of the touch. It's like having little digital eyes watching your every move on the screen. This method is excellent for enabling multi-touch and works with any object. Its real strength is scalability. It's a very cost-effective solution for creating very large interactive surfaces, like digital whiteboards or massive public information displays and interactive tables. Now, let's talk about the powerhouse behind most modern smart devices, projected capacitive, or PCAP, technology. Think of it as the supercharged version of the standard capacitive screen. Instead of just one conductive layer, PCAP screens use a grid of microfine wires or transparent electrodes, often arranged in a diamond pattern between 2 layers of glass. This grid generates a 3-dimensional electrostatic field. When a finger approaches or touches the surface, it alters the electrical field at multiple points in the grid. This allows the controller to detect touches with incredible accuracy and speed, and most importantly, to track multiple touch points simultaneously with ease. This is what gives you that fluid 10-finger multi-touch experience. PCAP screens are also extremely durable and scratch-resistant since the sensing grid is safely sandwiched behind a layer of glass. This technology is the gold standard for today's smartphones, tablets, and high-end industrial displays. Finally, we have a unique one called acoustic pulse recognition, or APR. This technology works by listening. When you tap the screen, your touch creates a tiny sound wave that propagates through the glass. Specialized sensors, called piezoelectric transducers, are placed at the corners of the screen. These sensors pick up the sound of the tap and convert that mechanical vibration into an electrical signal. By analyzing the unique sound signature and the time it takes for the pulse to reach each sensor, the system can determine the exact location of the touch. Because the screen is just a solid piece of glass, APR offers excellent durability and image clarity. However, its performance can be affected by ambient noise and vibrations in the environment, making it less suitable for loud or outdoor settings. You might find APR technology in some kiosks, gaming machines, and public information terminals where durability is key. So, what does the future hold for touch screens? The innovation isn't slowing down. We're on the cusp of flexible and foldable displays becoming mainstream, allowing our devices to change shape. Haptic feedback is getting more advanced, moving beyond simple vibrations to creating textures and sensations that make it feel like you're touching real buttons or surfaces. We're also seeing the development of fully transparent touch screens that could turn any window into an interactive display, as well as 3D touch systems that can sense how far your finger is from the screen. And with the rise of AI, gesture tracking will become even more sophisticated, allowing for more intuitive, touch-free interactions. Touch screens are evolving from simple, flat panels into truly intelligent and immersive interfaces that will redefine how we connect with the digital world. Thank you so much for watching. I hope this breakdown gave you a clearer picture of the incredible technology behind touch screens. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe and hit that notification bell so you won't miss our next tech deep dive. See you in the next one.